Welcome students. This is for the 5th semester students of B Farm. We are continuing the class about the instrumental application of phytochemical investigation, especially in characterization of the phytochemicals from herbal drugs and herbal formulations. So we should know about, especially we have seen last class about calorimetry, UV spectroscopy, and today we are going to see in this basic phytochemical investigation, phytochemistry after extraction by IR spectrophotometry. This is infrared spectrophotometry. So before going to the application, we should know the basic principle and basic instrumentation. Basic, how it's giving the band of the chromatogram and what is its relationship of identifying the functional groups. So this is the instrument. Even we have this instrument in our lab, in our institution. So students have to observe the instruments which is available and to know about how it is applied and how it is used, because most of the industries, they need students or the graduates who they appoint after the interview. They need the person should know how to handle the instruments. Even though they will give training, they should have an idea about the basic instrumental principles and how it has to be operated safely. This is about a spectrum. We should know infrared rays. It's also present in the normal light. That's why spectrum, the spectrum word is used. The infrared region of electromagnetic spectrum may be divided into three main sections: near, medium, far. Before that, we should know what all the rays which are there in the electromagnetic spectrum. You see here, the visible light is very, very small area in nanometer. From red to violet, you can see 750 to 400 nanometer. It's a small part which is visible radiation. The arrow which I am showing, you can see that very small, and we made it into in nanometer instead of showing in the centimeters of 10 to the power of minus 7. If you want to enlarge it, you can see very clearly 750 to 400 nanometer. It's a small part which is visible by our normal eye. And what about this next high level energy? We can see UV. Yesterday what we have discussed about UV, ultraviolet radiation, and next come X-rays, and next come gamma rays in higher energy level of electromagnetic spectrum. In just down to the visible, you will get immediately infrared radiation. Red, you might see infrared radiation. And then comes microwave, and then comes radio waves in lower energy levels. Today we are going to have the class about the infrared radiation, how it is applicable for the structural elucidation, or in fact directly we can say how it is useful and how it is applied in detecting the functional groups of our secondary metabolites present in the herbs and in the medicinal plants, or you can say it is secondary metabolites. See here, this infrared have three regions. The first one you can see, that is the near infrared region. The arrow you can see very clearly. The near infrared overtone region, it can be called 0.8 to 2.0 micron. The micron means actually the infrared measurements can be done 12,500 to 5,000 centimeter inverse. We are always telling in the other means, that is centimeter inverse. That is why by centimeters, like how you write BC. And here you see the second one is middle infrared region, that is vibrational rotational region. This place is the main place. This rays is maximum 2 to 15 micron region, or 5,000 to 666.66 centimeter inverse of the wavelength of rays in infrared is mostly used for this phytochemicals or the medicinal compound structural investigation of their vibrational rotational energy change can be obtained by this middle infrared vibrational rotational region. And number 3, far infrared region or rotational region. So vibration and rotation are the main concept behind when a light or when an infrared rays falls on an organic molecule. Yesterday when we were talking about UV, when a light falls on the organic molecule, it gets excited, and we have seen about the that oxochrome, which supports for the chromophore of a conjugated double bond system, which gives the absorption of the light of UV light. Here, this IR spectrum, the student should clearly, you can write and understand, very easy, simple. Electronic change in the organic molecule, modification, vibrational energy, rotational energy will happen in the middle IR region when it falls on the organic molecule. For region also, it gives rotational regional changes. Wavelength usually measured in centimeter inverse in IR, that is equal to 10 to the power of 4 by lambda in micrometer. We know 1 micrometer is equal to 10 to the power of minus 4 centimeter. That means 1 divided by 10,000. The main region of interest for analytical purpose, for the investigational purpose, for the structural elucidation purpose, for the identification of functional group purpose, is from 2.0 to 15 micron or micrometer, that is 4,000 to 400 waves per centimeter, that is centimeter inverse. The unit which is mentioned for IR spectrum is centimeter inverse. So that the graph or the band or the chromatogram which is obtained from the instrument, we can see the graph peak towards downwards. When infrared spectra IR interact with an organic molecules, the molecules or molecule absorbs specific frequency of IR radiation, leading to vibration of its bond. Leading to vibration of its bond. You know that pi bond, sigma bond are all present in it. That means single bond, double bond, triple bonds will be between two atoms in the molecules. So they have vibration will takes place, which can be used to identify functional groups and determine the molecule structures. So it's an important point, the student should know that. There are weaker bonds, stronger bonds, electronic configuration by pi bonds with electrons, clouding. So this energy utilized for their vibrational energy will differ by the presence of the atom, heavierness of the atom, complex system of the atoms. So these all will give the system to identify what type of functional group is present in it. So you can see this, a picture just to give an idea. When IR light of a source falls on the object, just a molecule, just a design we have told me in smaller classes, the teacher might have shown these models. So this bond, a single bond attached with an, you can imagine that is carbon with two hydrogen bond, are imaginary. So you can see frequency of absorption of the sample will be identified by the detector which you are using. And you can see the arrows, there is peaks also just shown for an identification. You can see the stretching of the bond, bending of the bond, opposite side stretching, asymmetric stretching, symmetric stretching can be seen in the small diagram. So this gives a different peaks due to the fall of the IR spectrum over the organic molecule. Different functional groups like carbon double bond O, carbonyl group, OH group, hydroxyl group, O bond with hydrogen or oxygen bond with hydrogen, carbon with hydrogen, CH, etc. C double bond H, C double bond O, CH, and you can see C double bond C. These all are there, bonded is there according to the structure attachment and as well as the bond attachment. The vibrational energy will differ when IR rays falls on the organic molecule. In organic molecule absorb the IR radiation at characteristic frequencies, resulting in specific absorption band or peaks in the IR spectrum. By analyzing the positions and intensities of these absorption bands, chemists, pharmacists can identify the functional groups present in an organic molecule. So a student can write at least a word, IR spectroscopy can give or identify the functional group of an organic molecule by means of its change made in their vibrational and rotational energy or electronic energy. Infrared spectra originate from the different modes of vibration and rotation of molecules. Molecule vibration can be made into two in infrared rays when they fall on organic molecule. Stretching and bending. What is this stretching and bending? Stretching vibration, stretching of the bond. is a rhythmical movement along the bond angle. Bond angle will be there. You might have seen there are many methane, ethane, propane, or you can say nitrogen means primary amine, secondary amine, tertiary amine, quaternary ammonium compound. They will be having the bonding of the hydrogen and carbon, or hydrogen and nitrogen. Nitrogen and hydrogen will be different in the bond angle. But stretching is, whatever the angle is not a problem. Stretching or pulling will be in the same line of the bond angle. It doesn't change the bond angle, but it rhythmically movement along the bond axis such that the interatomic distance is increasing or decreasing. The atom in this middle and the outer atom distance will be changed when IR spectrum or IR falls on the organic molecule. You can see this, an imaginary diagram. The number 1, it is stretching, that is asymmetrically, but antisymmetric compression is also possible. The hydrogen goes near to the oxygen. This is a water molecule, O2 hydrogen. The second one, anti-symmetric reaction is also possible. That's what just we want to show it. This is symmetric movement, both are stretching outwards, and here one is stretching outwards, one is going inside. You can see the picture. That's why I made a round to show you. So bending vibration also can be made. That angle like this also it can go. So the bending vibration due to IR rays falling on the organic molecule may consist of a change in bond angle. The bond angle will change towards down or up or opposite, like a scissoring can be possible, may consist of change in bond angle between bonds with a common atom or the movement of a group of atoms with respect to the remainder of the molecules without movement of the atom in the group with respect to one another. You can see this picture, symmetric pulling in the same direction, lengthening of the bond, but asymmetric opposite is also possible. Scissoring, that is bending opposite side, rocking one behind one, wagging above the plane, below the plane, twisting out the plane. One is down, one is up. So different types of bending is possible when an electromagnetic radiation IR falls on the organic molecule. I hope the student can understand very clearly. Imagine a structure what you studied in organic chemistry, and then think about R, S configuration, R configuration. This all you might have studied. A carbon atom attached with different molecules. You might have studied about chiral compound, dextrorotatory, levorotatory, many things. You have been advanced chemistry now. So it's properly, if you imagine, you can know that when IR rays falls on an organic molecule, what happens due to the vibration and the rotational energy change in the electronic configuration. That will give you the idea to write page together. Essay question also can be written. Example of twisting, rocking and torsional, that is scissoring and wagging, this, the picture which I have written there. Vibration involves a change in bond angle. This is just a picture to show you the chromatogram. Usually the IR will be in different manner, upside down, but we can see here this transition. I got IR spectrum of alcohol. OH will give a spectrum, a peak in 3500 to 3200 centimeter inverse, and you will get C bond O, because an ethanol will have CH3 OH. So there will be bond of C bonded with O also will be there. O bonded with hydrogen will also will be there. So it will be easy. You can get an intense peak due to C double bond O, not double bond. C bond O is 1260 to 1050 centimeter inverse of wavelength. You have a peak, and you can see there also I have shown for water, scissoring will take place of bending. You can see the scissoring will cause a peak in 1500 centimeter inverse, and OH peak you can see that 3500 to 3200, between that you are getting a peak, as you have seen in alcohol. You can see even in water also, because O bonded with hydrogen, it gives a peak in that area. So that's called similar bonding will give you the peak, and what type of functional group is present with other supportive peaks give you to identify. Some examples for the infrared absorption bands like CH, this gives stretching vibration calculated in 3400 centimeter inverse, that is 3.3 micron. And when it is hydrogen is replaced by deuterium, just an example to understand the presence of various molecule, how the changes you can find out. So that's what the researcher can identify. What is the other attachment of the molecule or attachment of the atom they can identify. So instead of hydrogen, just deuterium. If you give here, the stretching vibration is lower frequency due to the weakness of the deuterium. You can see this picture. You can see water is giving a peak due to the hydrogen with O bonding 3000 to 3500 between, you are getting the peak. At the same time, when hydrogen is replaced by deuterium, you see the peak. You are getting that intensity of absorption of IR spectrum in between 2300 to 2500 peak, that pink color. So this shows that the lambda or the peak absorption or the change in the vibrational energy or the bending energy differs due to the heaviness of the deuterium. Attachment of the atom, just an example. CC, C bond O, C to the N, C bond N. This all occurs in 1300 to 1800 centimeter inverse peaks. And C double bond O, C double bond nitrogen, N double bond O, nitrous O, in 1500 to 1900 centimeter inverse. C triple bond N, C triple bond C, they also give the peak in IR spectrum, that is 2300 to 2000 centimeter inverse. And for hydrogen attached with fluorine, HF, at 4138, not 400, 4138 centimeter inverse at high frequency, you can see the vibrational energy when hydrogen is attached with fluorine. Deuterium, it goes to heavy, but it goes to the lesser energy, but fluorine, when it is attached, it goes to the higher energy. See that difference. Fluorine is highly electronegative. So, dipole moment is high and also the force constant is more. So, these contain high frequency to absorb IR rays. OH hydrogen bonding decreases the stretching and increases the bending frequency for IR rays, IR absorption. That is why it is coming 3500 to 3000 range of centimeter inverse. So this is the instrument which is available in our lab. So what is the parts which is present in the instrument? And there is some difference in the UV spectrophotometer what you have seen, and here it is different. The materials like glass, quartz cannot be used here. Even though they are shown a prism, you should not think that is a glass prism. You cannot use, because glass, quartz, they all absorb IR rays. So in between it absorbs IR rays means your experiment will be completely damaged, or it will be wrong, because you cannot find how much it is absorbed by the instrumental defects. So you have to use always the material which is not hindering our experiment, or the source of the material. You can see here the source, they have put on light, but you are not going to use any tungsten lamp or mercury lamp or any type of hydrogen lamp will not emit IR spectrum. IR spectrum, you need a thermal wire, cadmium, that is for example metal wire, silicon, it has to burn and to produce IR. So the source is different from what the source you have used or studied in UV. Means we can say it is tungsten lamp can be used, for visible. For UV means we can say hydrogen lamp can be used. For fluorimetry we can use mercury lamp. For visible radiation even mercury lamp can be used. But here it is not so. So here there is comb which controls this IR rays which is coming from the source into the sampling area. Attenuator is also using, which is also controlling the rays with the two reflecting mirror. It comes inside this sampling area, and beam selecting or beam switching, where it will switch which beam have to pass through to the filter. And next come collimating mirror, which is giving to the prism, monochromator, or a grating. Here the student should remember, there in UV spectroscopy or UV spectrophotometry, we studied very clearly photometry is an instrument which will give optical instrument. There is an spectrometry, that is spectrometer, that is optical instrument which contain monochromator to give the light to fall on the sample, and then the detector. Here sample is kept mild, IR is fall on the sample, and then the light emitted after vibrational energy or rotational energy completing, the rays is taken by the monochromator, and then the detector is made. Opposite, the system is opposite to what you did in the UV spectrophotometry and the IR spectrometry. So here, that's what I want to remember. Again the student to make, I just made a circle. Source, not the tungsten light or the hydrogen light. Here wire temperature, that means by means of source is different of silicon wire, burnt, temperature control, emission of IR rays, comes to the sampling area where the sample of organic molecule interested to find out the functional group is kept there, and then it comes to the monochromator to identify the rays which is coming out from the sample, and then comes the detector. Detector is not by photomultiplier tube, don't write, it is not possible. It needs detector, different detector which can detect the IR rays, which is not UV or visible rays to be analyzed by photomultiplier tube. This is by different detector which can detect the IR rays. So that I have given some examples and not going in detail. The names at least the students should know. Now the attenuator and the comb, where you are controlling over the IR rays from the source, an attenuator reduces the intensity of the IR signal which is coming from the source, while a comb, often a laser frequency comb, provides a precise and stable wavelength reference for spectral measurement. It gives the stable rays to pass through the sample are the reference to give a constant comparison of what type of functional group is present in my unknown sample can be identified. Light source is used in IR spectroscopy is a glow bar. Glow bar, again repeating, you should remember, glow bar is used as a thermal light source for infrared spectroscopy. It is silicon carbide. In last slide also, when I was explaining, I was telling about silicon carbide rod of 5 to 10 millimeter width and 20 to 50 millimeter length, which is electrically heated up to 1000 to 1600 centimeter, sorry, not centimeter, 1000 to 1650 degrees centigrade, or in Fahrenheit you can say 1830 to 3000 degree Fahrenheit temperature should be maintained for this silicon carbide rod, which will emit IR rays. And the important point to be considered is glass or quartz material cannot be used inside the instrument, even including the cuvette or the probe which you have used to supply the sample even. Glass and quartz absorbs strongly in the IR region, and the photomultiplier detector cannot be used or insensitivity to IR radiation. Front surfaces of the mirror which is used is largely employed to avoid the necessity of the radiation passing through glass. Mirrors are used. It should not pass through the glass. Or quartz layer or reflection from metallic surfaces is very efficient in infrared region. In infrared spectroscopy, prisms are typically made up of material like rock salt. What is rock salt? Sodium chloride. Simple, made up of sodium chloride prisms. For large wavelength, other infrared transparent materials like potassium bromide KBr or thallium bromoiodide KRS5 is used. So this also the students should remember the point in IR spectroscopy. In IR spectroscopy, detectors like pyroelectric detectors, photoconductive detectors, we are not using photomultiplier, photoconductive detectors and thermal conductive detectors are used to convert the absorbed IR radiation into measurable electrical signal by using pyroelectric detector, by using photoconductor, which will convert the emission of rays to electric current. So this is what the thermoelectric detector, thermodetectors are also can be used. What is this? The lead sulfide detector is used for near infrared region of spectrum. For mid and far radiation, mercury cadmium telluride detector is used. Telluride. Mercury cadmium telluride or telluride detector are used. This is that detector. Lead sulfide detector, and this is the mercury cadmium telluride detectors. This will give the impulse of the change in the vibrational energy, the change in the bending and stretching of the bond will be given to the computer. The database will give you very clear picture of a chromatogram. Examples, you can see the chromatogram which is obtained. Just an example for allyl alcohol. Allyl means CH, double bond CH will be there. Allyl alcohol, not directly ethyl alcohol. So just you can take a graph to get, you can see there is a fingerprint area. You can start a peak of 920 centimeter inverse and you will get 990 centimeter inverse due to OH stretching deformation in 1200. Usually OH will get in, as you have seen there is stretching 1330 centimeter inverse which I have shown there. This is 1020 due to deformation, and you will get a peak of 1650 due to C double bond C, because allyl alcohol. Normal alcohol you will not get this peak of 1650 centimeter inverse due to the presence of C double bond C bonding. And OH, almost we know that peak which is due to the stretching of 3300 centimeter inverse. In the beginning itself I have just explained. To know about these peaks and what is IR spectroscopy, the student, if they listen 100% sure, there is no need to read any book or anything. You can write for 5 mark question by means of listening to this. What type of stretching, bending will take place in an organic molecule when IR rays falls on them. And allyl alcohol, an example by means of taken C double bond C, an additional peak will be there for 1650 centimeter inverse. A region with a low frequency of 400 to 1400 centimeter inverse in the IR spectrum is called as fingerprint region. So I was asking, even when I was studying also, I have a doubt. What is this fingerprint region? What is this fingerprint region? See, that fingerprint region means the region from the 1300 to 1500. You can see there is a peaks which is obtained, which can be easily kept with a standard and a sample. Similar structure, similar component like benzene, if they have an aromatic compound, they have this similar fingerprint region. And similar compound, if they are, you can identify with a known and unknown, like how you detect the DNA fingerprinting in electrophoresis, finding out who is the culprit, can also be identified by comparing with the sample and the standard or a marker. So you can see that CH bond is giving a peak, and a fingerprint region also we can see that very clearly. So similar to a human fingerprint, the same fingerprint which is identified by the forensic department by IR, the pattern absorbance band will be similar in the fingerprint region is characterized of the compound as a whole. Even two different molecules have the same functional group, their IR spectrum will not be identical, and such a difference will be reflected in the bands of the fingerprint region. So it will give, this is not the compound which we have identified, this is a different one, or this is the same one, can be decided by fingerprint. Therefore, the IR form of an unknown sample can be compared to a database of an IR spectrum of a known standard to confirm the identity of the unknown sample. This is the principle for any fingerprinting. Application of IR spectrum or IR spectroscopy, just 2 slides. I made only the line. Identification of functional group and structural elucidation. The entire IR region is divided into group frequency region 400 centimeter inverse to 1500 centimeter inverse. Fingerprint region is 1500 centimeter inverse to 4000 centimeter inverse. In group frequency region, the peak corresponding to different functional group can be absorbed, example amino group, alcoholic group, etc. In fingerprint region, many skeletal variation which are typical for the molecules as a whole and characteristic peak are absorbed. Hence, this region of IR spectrum is called as fingerprint region of a molecule. Number 2, identification of a drug substrate or a drug substance can be done. IR spectrum of a sample and a standard can be compared to identify a substance. If the spectra are same, then the identity of the sample can be confirmed. This technique is called spectral matching technique. Identifying the impurities in a drug sample. Impurities have the different chemical nature when compared to a pure drug. Hence, these impurities give rise to additional peaks than that of the pure drug. By comparing these, we can identify the presence of impurity. Number 4, study of hydrogen bonding, whether it is intermolecular or intramolecular type. Study of polymers, ratio of cis and trans isomers in mixture of compounds. Quantitative analysis. The quantity of the substance can be determined either in pure form or as mixture of two or more components. In this, the peak which is characteristic for the drug is chosen and a comparison of the area of the peak and the standard and the sample is done. This method is called as baseline technique and is then used to determine the quantity of the substance. So interesting instrument. Kindly listen to that. There is lots of parameters are there. But in this junction we need what is IR spectroscopy, how it is applicable for herbal formulation and herbs and identifying or characterizing medicinal compounds or the synthetic or natural structure elucidation of a chemistry background of a structure can be functional group can be done very clearly by IR spectroscopy. Kindly use of it. Thank you.